What if I told you that the screen you're staring at right now doesn't actually exist until you look at it? That the photons carrying these words to your eyes were traveling as ghostly waves of pure possibility until the moment your consciousness collapsed them into the solid reality you think you see. In 1909, a simple experiment with light and two tiny slits revealed the most disturbing truth in the history of science. Reality exists in a state of infinite potential until observation forces it to choose just one form. But here's what will shatter everything you believe about existence. Quantum physicists have discovered that the fundamental building blocks of your body, your thoughts, and everything you've ever touched don't exist as solid particles until they're measured. They exist as waves of possibility spreading through dimensions you can't imagine. Tonight, we'll explore how the act of looking might be the cosmic force that creates the universe itself. Chapter 1. The Ancient Mystery of Light's Nature. The story of light begins with humanity's most ancient mystery. For thousands of years, human beings have gazed up at the sun, watched fire dance in darkness, and wondered what this invisible force could possibly be. Light reveals every color, every texture, every face you've ever loved, yet light itself remains completely invisible. You can see everything except the very thing that makes seeing possible. This paradox haunted the greatest minds in history and led them down a path that would eventually reveal the most shocking truth about reality itself. In the bustling marketplaces of ancient Greece, where philosophers gathered to debate the nature of existence, some of the first scientific theories about light were born. These early thinkers didn't have laboratories or sophisticated equipment. They had only their minds, their observations, and an unquenchable curiosity about how the world actually worked. What they discovered would echo through the centuries and eventually crack open the deepest secrets of the universe. Pythagoras, the mathematician famous for his theorem about triangles, proposed something that sounds almost backwards to us today. He believed that vision worked because light rays shot out from your eyes and struck the objects you wanted to see. Imagine tiny invisible arrows firing from your pupils every time you glanced at something. To Pythagoras, seeing was an active process where your eyes reached out and touched the world with beams of light. This wasn't just a wild guess. It actually explained some puzzling observations. If you've ever shined a flashlight and noticed how the beam seems to point exactly where you're looking, you can understand why this idea made sense to ancient minds. But not everyone agreed with Pythagoras. Epicurus, another Greek philosopher, argued for exactly the opposite idea. He claimed that objects themselves produced light rays which then traveled to your eyes. This sounds much more familiar to us now, but imagine how radical this was at the time. Epicurus was suggesting that every single thing you can see is constantly shooting invisible particles in all directions, and vision happens when some of these particles happen to hit your eyes. Think about how many objects surround you right now, and imagine all of them firing tiny invisible bullets of light in every possible direction every single moment. The universe would be filled with an unimaginable storm of these light particles, yet somehow they don't interfere with each other or slow each other down. Other Greek thinkers like Euclid and Ptolemy took a more practical approach. Instead of worrying about whether light came from eyes or objects, they focused on how light actually behaved. They created the first ray diagrams, drawing straight lines to show how light bounced off mirrors and bent when passing through water or glass. These diagrams worked perfectly for predicting where light would go and how images would form. For these early scientists, light was simply a ray, a straight line moving from one point to another. This ray theory explained so many observations that it dominated human thinking about light for over 1,000 years. But there was something deeper brewing in these ancient ideas. Lucretius, a Roman philosopher who followed the teachings of Democritus, believed that everything in the universe was made of tiny indivisible pieces called atoms. To Lucretius, light had to be made of atoms too. He imagined streams of light particles flowing from the sun in perfectly straight lines. When these particles encountered objects, They created the sharp-edged shadows you see every day. This particle theory of light seemed to explain everything. Shadows had sharp edges because light particles traveled in straight lines and couldn't bend around corners. Bright lights were simply places where more light particles were concentrated. Darkness was just the absence of these particles. During the 10th century, while Europe was struggling through what we call the Dark Ages, incredible advances in understanding light were happening in the Islamic world. A brilliant mathematician named Ibn al-Haytham, known in the West as Al-Hazen, wrote a revolutionary book called the Book of Optics in 1027. This wasn't just another philosophical debate about light. Ibn al-Haytham actually performed experiments. He built devices, made careful measurements, and tested his ideas against reality. His book was the first truly scientific treatment of light, covering everything from how the human eye works to the mathematical laws governing lenses and mirrors. Ibn al-Haytham's work was so advanced that it wouldn't be matched in Europe for another 500 years. He understood that light traveled at finite speed, he explained how rainbows formed, and he even described what we now call the camera obscura. But perhaps most importantly, he established the experimental method that would eventually lead to modern science. He showed that understanding light required more than just thinking about it. You had to test your ideas against the real world. But it was Isaac Newton, the towering genius of the 17th century, who would create the most influential theory of light in human history. Newton had already revolutionized our understanding of motion and gravity. His mathematical laws could predict the movements of planets, the trajectory of cannonballs, and the swing of pendulums with incredible precision. When Newton turned his attention to light, he brought the same mathematical rigor that had made him the most celebrated scientist in Europe. Newton's particle theory of light was elegant and powerful. He imagined light as a continuous stream of tiny particles flowing from luminous objects in all directions. These light particles, which he called corpuscles, behaved exactly like tiny balls bouncing off surfaces. When light reflected from a mirror, Newton explained it just like a tennis ball bouncing off a wall. The ball hits the surface at a certain angle and bounces back at exactly the same angle. This simple idea explained the ancient law of reflection that had puzzled thinkers for centuries. Newton showed this mathematically by breaking the motion of light particles into horizontal and vertical components. When a light particle hits a reflecting surface, the horizontal part of its motion stays the same, but the vertical part reverses direction. The mathematics worked out perfectly, giving the famous law that the angle of incidence equals the angle of reflection. Newton had taken a mysterious property of light and explained it with the same mechanical principles that governed everything else in the universe. But Newton's genius went even further. He tackled the puzzle of refraction, the bending of light when it passes from air into water or glass. You've seen this effect every time you looked at a stick partially submerged in water. The stick appears bent at the water's surface, even though you know it's perfectly straight. Newton explained this by proposing that matter exerted a force of attraction on light particles. When light moved through air, the forces on all sides balanced out, so the particles traveled in straight lines. But at the boundary between air and glass, the forces became unbalanced, and the light particles were pulled toward the denser material. This force changed the speed and direction of the light particles, causing them to bend toward the perpendicular as they entered the glass. The mathematics of this process explained why objects appeared distorted when viewed through water and how lenses could focus light to create images. Newton's particle theory seemed to explain every known property of light with mechanical precision. For over 150 years, Newton's particle theory dominated scientific thinking about light. This wasn't just because the theory worked well, though it did. Newton had become such a towering figure in science that most researchers simply assumed he must be correct about light too. After all, his laws of motion and gravity had been so spectacularly successful at explaining and predicting everything from falling apples to orbiting planets that questioning Newton felt almost like questioning the laws of nature themselves. But there were problems lurking beneath the surface of Newton's beautiful theory. The particle theory predicted that light should travel faster inside dense materials like glass than in air. This seemed backwards to many thinkers, but it couldn't be tested with the technology of Newton's time. The theory also suggested that luminous objects should gradually lose mass as they continuously emitted streams of light particles. For something as bright as the sun, this mass loss should be enormous, yet no one observed the sun getting smaller. Most troubling of all, Newton's particle theory couldn't explain what happened when light passed through very narrow openings. Instead of casting sharp shadows as particles should, light spread out and created complex patterns of bright and dark bands. This phenomenon, called diffraction, seemed to demand a completely different explanation. While Newton was developing his particle theory, a Dutch astronomer named Christian Huygens was pursuing a radically different approach. Huygens had studied the properties of sound and knew that sound was definitely a wave phenomenon. Sound could bend around corners, create interference patterns, and travel through materials at different speeds. Huygens wondered if light might be a wave too, similar to sound, but traveling through a different medium. Huygens proposed that all of space was filled with a mysterious substance he called the ether. This ether was supposed to be completely transparent and massless, yet still capable of transmitting waves of light. According to Huygens, when something glowed, it created vibrations in the ether that spread outward like ripples on a pond. These ether waves carried energy through space until they reached your eyes, where they were somehow converted into the sensation of sight. The key insight of Huygens' theory was his principle of wavefronts. He imagined that every point on a moving wave of light acted like a new source, creating tiny wavelets that spread out in all directions. These countless wavelets combined to form the next wavefront, which then repeated the process. This wave picture explained how light could bend around obstacles and spread out when passing through narrow openings. It also explained how light waves could interfere with each other, creating the complex patterns that particle theories couldn't handle. Huygens used his wave theory to explain both reflection and refraction just as successfully as Newton had with particles. When light waves hit a reflecting surface, they bounce back with the wavefronts maintaining their shape, but reversing direction. When light passed from air into glass, the waves slowed down, causing them to bend toward the perpendicular. The mathematics worked perfectly, and the wave theory actually predicted the correct relationship between light speed and the density of materials. Despite the success of Huygens' wave theory, it was largely ignored for over a century. Newton's reputation was simply too powerful, and the idea of an invisible ether filling all of space seemed too mysterious for most scientists to accept. The wave theory also couldn't explain some observations that seemed to favor particles, such as the way light appeared to travel in perfectly straight lines and cast sharp shadows in most circumstances. But the wave theory of light was waiting in the wings, ready to challenge Newton's particle picture when the right experiments finally came along. The stage was set for one of the greatest revolutions in the history of science, a revolution that would reveal that light was far stranger and more wonderful than either Newton or Huygens had ever imagined. The battle between wave and particle theories of light was really a battle between two completely different ways of understanding reality itself. Particles represented the mechanical worldview where everything could be explained by the motion and collision of tiny solid objects. Waves represented a more mysterious reality where energy and information could flow through space without requiring any actual substance to carry them. Neither Newton nor Huygens could have imagined that this ancient debate about the nature of light would eventually lead to the discovery that reality itself might exist in a state of pure possibility until consciousness observes it into existence. As we stand on the shoulders of these giants and look back at their struggle to understand light, we can see the first hints of the mind-bending revelation that was coming. The universe was preparing to reveal that the distinction between wave and particle, between potential and actual, between observer and observed, was far more fundamental and mysterious than anyone had ever dreamed. Chapter 2: Young's Revolution. When light revealed its secret. As the 18th century gave way to the 19th, Isaac Newton's particle theory of light seemed unshakable. The great man had been dead for nearly a century, but his scientific legacy cast such a long shadow that questioning his ideas about light felt almost like heresy. Universities across Europe taught Newton's corpuscular theory as established fact. Textbooks explained how tiny particles of light bounced off mirrors and bent through lenses with the same mechanical precision that governed falling rocks and orbiting planets. The scientific establishment had settled into comfortable certainty about the nature of light, confident that the mystery had been solved once and for all. But in 1801, a young English physician and natural philosopher named Thomas Young was about to shatter that certainty forever. Young wasn't even primarily a physicist. He was a medical doctor who studied the human eye, a linguist who helped decode ancient Egyptian hieroglyphs, and a polymath whose curiosity seemed to embrace every corner of human knowledge. Perhaps it was precisely because he wasn't trapped within the rigid thinking of professional physicists that Young could see what others had missed. Sometimes, the most profound discoveries come from outsiders who dare to question what everyone else accepts as obvious truth. On November 24th, 1801, Young presented a paper to the Royal Society of London that would change everything. The paper was titled On the Theory of Light and Colours, and it described a series of experiments so simple that anyone could repeat them, yet so profound that they challenged the entire Newtonian worldview. Young hadn't built elaborate apparatus or spent years collecting data. He had simply looked at light more carefully than anyone before him. And in that careful looking, he discovered something that would echo through the centuries and eventually lead to the most mind-bending revelations about the nature of reality itself. Young's first experiment was almost childishly simple. As he wrote in his own words, "I made a small hole in a window shutter and covered it with a piece of thick paper, which I perforated with a fine needle." Picture Young in his study, sunlight streaming through a tiny pinhole, casting a sharp beam across his darkened room. This wasn't unusual. People had been using pinholes to study light for centuries, but what Young did next was revolutionary. He brought a thin card, about 1/30th of an inch wide, into the beam of light and observed its shadow. According to Newton's particle theory, this should have created a simple shadow with sharp edges. Just like the shadow cast by any solid object when particles are blocked from reaching a surface, the light particles should have traveled in perfectly straight lines until they hit the card, creating a clear boundary between light and dark regions. This is exactly what our everyday experience suggests should happen. When you hold your hand up to block sunlight, you get a hand-shaped shadow with reasonably sharp edges. The particle theory of light explained this perfectly and predicted exactly the same thing should happen with Young's thin card. But that's not what Young observed. Instead of a simple shadow with sharp edges, he saw something that should have been impossible, according to Newton's theory. Young described his observations by writing that we may infer that homogeneous light at certain equal distances in the direction of its motion is possessed of opposite qualities capable of neutralizing or destroying each other, and of extinguishing the light where they happen to be united. Young had discovered that light could somehow cancel itself out, creating regions of darkness where two beams of light came together. This was the first clear evidence of what we now call the principle of superposition, one of the most fundamental properties of waves. When two waves meet, they don't just pass through each other unchanged like particles would. Instead, they combine according to a simple rule. If the peaks of both waves arrive at the same point at the same time, they add together to create a bigger wave. This is called constructive interference. But if the peak of one wave arrives at the same time as the trough of another wave, they cancel each other out completely. This is called destructive interference. Young realized that he was seeing interference patterns, the unmistakable signature of wave behavior. The thin card wasn't just blocking light particles like a solid barrier. It was somehow causing the light to bend around its edges and interfere with itself. The regions of darkness in the shadow weren't caused by the absence of light particles. They were caused by light waves cancelling each other out through destructive interference. Light was literally destroying itself through a mathematical process that only made sense if light was a wave phenomenon. But Young's most famous experiment was yet to come. Building on his observations of single-slit diffraction, he designed what would become known as the double-slit experiment, arguably the most important experiment in the history of physics. The setup was elegantly simple. Young took a beam of sunlight and passed it first through a single, narrow slit to make it spread out and become more uniform. This diffracted light then illuminated two parallel slits placed very close together. Each slit acted like a new source of light waves, creating two overlapping beams that spread out and eventually hit a screen where Young could observe the pattern. If light consisted of particles, as Newton claimed, the result should have been straightforward. Some particles would pass through the first slit, some through the second slit, and they would create two bright regions on the screen corresponding to the two openings. There might be some spreading due to the particles bouncing off the edges of the slits, but basically, you would expect to see two bright strips with a dark region between them where no particles could reach. What Young actually observed was completely different and utterly shocking to anyone who believed in Newton's particle theory. Instead of two bright regions, Young saw multiple alternating bands of light and darkness across the entire screen. These interference fringes, as they came to be called, were the unmistakable signature of two waves overlapping and interfering with each other. Where the waves arrived in phase, with their peaks and troughs aligned, they created bright bands through constructive interference. Where they arrived out of phase, with the peak of one wave meeting the trough of another, they created dark bands through destructive interference. The mathematics of this interference pattern was beautiful and precise. Young could calculate exactly where the bright and dark bands should appear based on the wavelength of light, the distance between the slits, and the distance to the screen. The formula predicted the spacing of the fringes with perfect accuracy. This wasn't just a qualitative observation that light seemed wave-like. It was quantitative proof that light was a wave phenomenon with a specific wavelength that could be measured with remarkable precision. Young's experiments revealed that different colors of light had different wavelengths. Red light created interference patterns with wider spacing between the fringes, indicating a longer wavelength. Blue light created patterns with narrower spacing, indicating a shorter wavelength. For the first time in human history, the mysterious quality we call color could be understood as a fundamental physical property, the wavelength of electromagnetic oscillations. The rainbow wasn't just a pretty display of nature's artistry. It was a spectrum of different wave frequencies, each creating its own unique interference signature. But the implications went far deeper than just measuring wavelengths. Young's double-slit experiment revealed something profoundly disturbing about the nature of reality itself. The light passing through the two slits was somehow interfering with itself. This meant that individual rays of light were not traveling as discrete particles along definite paths as Newton had imagined. Instead, light seemed to be exploring multiple paths simultaneously, like a wave that could spread out and sample many different routes through space at the same time. Think about what this really means. When light encounters the two slits, it doesn't choose one slit or the other like a particle would have to do. According to the wave picture, light passes through both slits simultaneously, creating two overlapping waves that interfere with each other on the far side. The light somehow knows about both slits at once and adjusts its behavior accordingly. If you block one slit, the interference pattern disappears completely, even though you haven't changed anything about the light going through the other slit. This suggests that light carries information about the entire experimental setup, not just the local conditions it encounters. Young's discovery created a crisis in physics that would take more than a century to fully resolve. The wave nature of light explained interference and diffraction perfectly, but it couldn't explain other well-established properties of light that seemed to demand a particle description. Light still traveled in straight lines most of the time, still cast sharp shadows under normal circumstances, and still seemed to carry energy in discrete packages that could knock electrons out of metals. The wave theory explained some observations beautifully while completely failing to account for others. The scientific community's reaction to Young's work was initially hostile. Newton's reputation was so overwhelming that many physicists simply refused to believe the experimental results. They argued that Young must have made errors in his observations, or that some unknown factor was interfering with his measurements. The idea that the great Newton could have been fundamentally wrong about the nature of light seemed almost unthinkable to minds trained in the Newtonian tradition. Some critics attempted to explain Young's results without abandoning the particle theory. They proposed complex mechanisms by which light particles might interact with the slits to create patterns that resembled wave interference. These explanations became increasingly contrived and unsatisfying as more experiments confirmed Young's observations. It gradually became clear that no amount of clever reasoning could force the particle theory to explain the wave-like behavior of light in interference experiments. As the 19th century progressed, more and more evidence accumulated in favor of the wave theory of light. Scientists discovered that light could be polarized, showing that light waves oscillated in directions perpendicular to their motion, just like waves on a string. They found that light traveled more slowly in dense materials than in air, confirming a key prediction of wave theory and contradicting Newton's particle model. They discovered electromagnetic induction and began to understand light as a form of electromagnetic radiation, waves of electric and magnetic fields propagating through space at incredible speed. The work of scientists like Augustin Jean Fresnel, who developed the mathematical theory of wave optics, and James Clerk Maxwell, who showed that light was an electromagnetic wave, seemed to settle the question definitively. By the end of the 19th century, the wave theory of light had triumphed completely. Newton's particle theory was relegated to the dustbin of scientific history, a noble attempt that had been superseded by a deeper understanding of nature. Light was a wave phenomenon, pure and simple. The universe was filled with an electromagnetic field that could support oscillations at different frequencies. What we called light was just the small portion of this electromagnetic spectrum that human eyes happen to be sensitive to. Radio waves, microwaves, infrared radiation, visible light, ultraviolet light, X-rays and gamma rays were all the same basic phenomenon, electromagnetic waves differing only in their frequency and wavelength. The mystery of light had been solved once and for all, or so it seemed, but nature had one more surprise waiting. Even as physicists celebrated their complete understanding of light as an electromagnetic wave, new experiments were beginning to reveal phenomena that the wave theory couldn't explain. The photoelectric effect, blackbody radiation, and atomic spectra all suggested that light carried energy in discrete packets, exactly as Newton's discarded particle theory had proposed. The wave-particle debate that seemed settled was about to explode into something far stranger and more profound than either Newton or Young could have imagined. Young's simple experiment with two slits had done more than just prove that light was a wave. It had opened a window into a deeper level of reality where the familiar categories of wave and particle began to break down. The interference patterns Young observed were the first glimpse of a universe that exists in multiple states simultaneously until the act of observation forces it to choose just one reality. The dark and bright fringes on Young's screen were early evidence that the universe might be far stranger than anyone had ever dreamed. A place where the very act of looking changes what you find. In retrospect, we can see that Young's double-slit experiment was the first step toward discovering that reality itself might be wave-like, existing in a state of superposition until consciousness collapses it into definite experience. The mathematics of interference that Young discovered would eventually evolve into the probability waves of quantum mechanics. where particles exist as clouds of possibility until measurement forces them to appear at specific locations. The wave function that governs this process follows the same principles of superposition that Young first observed in his simple experiments with light and slits. As we look back at Young's revolutionary work, we can appreciate how a simple question about the nature of light led to insights that would eventually transform our understanding of reality itself. Young didn't just discover that light was a wave. He discovered the first evidence that the universe operates according to principles far more mysterious and beautiful than the mechanical clockwork that Newton had envisioned. The interference patterns dancing across Young's screen were the first visible proof that consciousness and reality are connected in ways that still challenge our deepest assumptions about the nature of existence. Chapter 3: Einstein's Quantum Revolution: Light as Particle Redux. By the dawn of the 20th century, physicists thought they had finally solved the ancient mystery of light. Thomas Young's double-slit experiments had decisively proven that light was a wave phenomenon. James Clerk Maxwell had shown that these waves were oscillations of electric and magnetic fields propagating through space at incredible speed. The mathematics was elegant, the predictions were accurate, and the wave theory of light seemed to explain every known property of electromagnetic radiation. Universities taught wave optics as established fact, and textbooks confidently proclaimed that the nature of light was no longer a mystery. But nature was preparing to deliver the most shocking surprise in the history of physics. Deep within the behavior of light lay secrets that would not only resurrect Newton's discarded particle theory, but transform it into something far stranger than anyone had ever imagined. The story of this revolution begins with a puzzle that seemed almost mundane at first, but would eventually crack open the foundations of reality itself. The puzzle was called the black-body radiation problem, and it emerged from the practical concerns of the industrial age. As engineers worked to build better light bulbs and more efficient furnaces, they needed to understand exactly how hot objects radiated energy. When you heat a piece of metal, it first glows red, then orange, then yellow, and finally white hot as the temperature increases. This wasn't just a curious observation. It was a fundamental process that governed everything from the light of stars to the warmth of your own body. Physicists created an idealized object called a black body, something that would absorb all radiation falling on it and emit radiation with a spectrum that depended only on its temperature. They expected that the well-established laws of classical physics would easily predict how much energy such an object would radiate at each wavelength. The mathematics seemed straightforward, involving nothing more complicated than the statistical behavior of electromagnetic waves in thermal equilibrium. But when scientists actually measured the radiation from real black bodies and compared it to the predictions of classical theory, they discovered something deeply disturbing. The classical calculations predicted that hot objects should radiate infinite amounts of energy at short wavelengths. This became known as the ultraviolet catastrophe because it suggested that every hot object should blast out unlimited amounts of ultraviolet light, X-rays, and gamma rays. Obviously, this wasn't happening. Hot objects glowed with predictable colors and radiated finite amounts of energy, not the infinite catastrophe that classical physics demanded. For years, physicists struggled to understand this discrepancy. They tried modifying their assumptions, checking their mathematics, and proposing new mechanisms, but nothing worked. The ultraviolet catastrophe seemed to reveal a fundamental flaw in the classical understanding of electromagnetic radiation. Either the experimental measurements were wrong, which seemed unlikely given how carefully they had been performed, or classical physics was missing something essential about the nature of light and energy. In 1900, a German physicist named Max Planck was working desperately to solve this puzzle. Planck was a conservative scientist who deeply respected the established laws of classical physics and had no desire to revolutionize anything. He was simply trying to find a mathematical formula that would fit the experimental data for black-body radiation. What he discovered would change everything, though at first, Even Planck himself didn't fully understand the implications of his own work. Planck found that he could make the mathematics work perfectly if he made one bizarre assumption. Instead of allowing electromagnetic energy to be emitted and absorbed in any amount, as classical physics suggested, Planck assumed that energy could only be exchanged in discrete packets. These packets, which he called quanta, had an energy that was proportional to the frequency of the radiation. The constant of proportionality, now known as Planck's constant, was an incredibly tiny number, but it was fundamental to making the theory work. This quantum hypothesis seemed to violate everything physicists thought they knew about energy. In the classical world, energy was continuous. You could have any amount of energy you wanted, just like you could have any amount of water by filling a container to any level. But Planck was suggesting that energy came in indivisible units, like coins in an economy where you couldn't have fractions of a penny. At low frequencies, these energy quanta were so small that they seemed continuous, just as a handful of sand seems smooth even though it's made of discrete grains. But at high frequencies, the quantum nature of energy became important and prevented the ultraviolet catastrophe. Planck's quantum formula worked perfectly. It predicted the observed spectrum of blackbody radiation with incredible accuracy across all wavelengths and temperatures. The ultraviolet catastrophe disappeared because high-frequency radiation required such large energy quanta that thermal energy couldn't easily excite these modes. But Planck himself was deeply uncomfortable with his own discovery. He spent years trying to find a way to derive the same results using classical physics, hoping that the quantum hypothesis was just a mathematical trick that could eventually be eliminated. It was Albert Einstein who recognized that Planck's quantum hypothesis revealed something profound about the fundamental nature of light itself. In 1905, the same miraculous year in which he published his special theory of relativity, Einstein wrote a paper that would resurrect Newton's particle theory of light in a completely new form. The paper was titled Concerning a Heuristic Point of View about the Creation and Transformation of Light, and it would eventually earn Einstein the Nobel Prize in Physics. Einstein was studying another puzzling phenomenon called the photoelectric effect. When light shines on certain metals, it can knock electrons out of the surface, creating an electric current. This effect was already being used in primitive photoelectric cells, but its detailed behavior made no sense according to the wave theory of light. Classical physics predicted that brighter light should give the ejected electrons more energy, since brighter light meant more intense electromagnetic waves. But experiments showed something completely different. The energy of the ejected electrons depended only on the color of the light, not its brightness. Blue light ejected electrons with high energy, while red light ejected electrons with low energy, regardless of how bright either beam was. Even more puzzling, there was a threshold effect. Below a certain frequency, no amount of light could eject any electrons at all, no matter how bright the beam became. This made no sense if light was a continuous wave that could deliver any amount of energy over time. Einstein realized that the photoelectric effect could be explained perfectly if light consisted of discrete packets of energy, exactly as Planck's quantum hypothesis suggested. Einstein proposed that light was composed of particles, which he called light quanta, and which we now know as photons. Each photon carried a definite amount of energy proportional to its frequency, given by Planck's formula. When a photon hit an electron in the metal, it transferred all of its energy in a single, instantaneous collision, like a billiard ball striking another ball. This photon picture explained all the puzzling features of the photoelectric effect immediately. The energy of ejected electrons depended only on the frequency of light, because that determined the energy of individual photons. Brightness corresponded to the number of photons, not their individual energies. So brighter light ejected more electrons but didn't change their individual energies. The threshold effect occurred because electrons needed a minimum energy to escape from the metal, and photons below a certain frequency simply didn't carry enough energy to liberate electrons, no matter how many of them there were. Einstein's photon theory was revolutionary, but it created a new crisis in physics. Light seemed to be simultaneously a wave and a particle, depending on which experiment you performed. Young's double-slit experiment clearly showed wave behavior with interference and diffraction. The photoelectric effect clearly showed particle behavior with discrete energy packets and instantaneous collisions. Both experiments were carefully performed and impossible to dismiss, yet they seemed to demand contradictory explanations. This wave-particle paradox became even more confusing as additional experiments confirmed both aspects of light's behavior. Arthur Compton's experiments in the 1920s showed that X-rays scattered off electrons exactly like particles, colliding with other particles. When an X-ray photon hit an electron, both objects recoiled according to the laws of conservation of energy and momentum, just as Newton's mechanics predicted for particle collisions. Compton could even measure the change in the X-ray's wavelength after the collision and found perfect agreement with the particle prediction. But other experiments continued to confirm the wave nature of light. Scientists discovered that light could be polarized, showing that light waves oscillated in specific directions perpendicular to their motion. They found that different wavelengths of light refracted by different amounts when passing through prisms, creating the beautiful spectra that revealed the composition of distant stars. Interference and diffraction effects could be observed with any form of electromagnetic radiation, from radio waves to gamma rays, all following the same wave equations that Maxwell had derived. The paradox seemed impossible to resolve. How could light be made of discrete particles and still create the smooth interference patterns of wave behavior? If light consisted of photons flying through space like tiny bullets, how could they interfere with each other to create the alternating bright and dark bands that Young had observed? Particles don't interfere with each other in the same way that waves do. They collide, bounce off each other, or pass by without interaction, but they don't create the mathematical superposition effects that waves exhibit. Some physicists tried to resolve the paradox by proposing that light was made of particles that somehow guided themselves along wave-like paths. Others suggested that light was fundamentally wave-like, but appeared particle-like under certain experimental conditions. These attempts to reconcile wave and particle pictures led to increasingly complex and unsatisfying explanations that failed to address the core mystery. The breakthrough came when physicists realized that the wave-particle paradox wasn't a problem to be solved, but a fundamental feature of reality that needed to be accepted. Light wasn't sometimes a wave and sometimes a particle. It was something entirely new, a quantum object that exhibited both wave and particle properties depending on how you chose to observe it. This insight would eventually lead to the development of quantum mechanics, a new framework for understanding nature that would revolutionize not just physics, but our entire conception of reality. Einstein's photon theory had done more than just explain the photoelectric effect. It had revealed that energy itself came in discrete, indivisible packets at the most fundamental level. This quantum nature of energy would prove to be one of the most important discoveries in the history of science, leading to technologies like lasers, computer chips, and quantum computers that rely on the precise control of individual photons and electrons. But Einstein himself remained deeply troubled by the implications of his own discovery. The quantum nature of light seemed to introduce an element of randomness into physics that violated his belief in a deterministic universe. When a photon hits a photoelectric surface, quantum mechanics can only predict the probability that an electron will be ejected, not whether any particular collision will actually liberate an electron. This probabilistic character of quantum events led Einstein to his famous declaration that God does not play dice with the universe. The wave-particle duality of light also raised profound questions about the nature of observation and measurement. The experimental setup seemed to determine whether light exhibited wave or particle behavior. In interference experiments, light behaved like a wave. In photoelectric experiments, light behaved like a particle. This suggested that the act of measurement itself might play a fundamental role in determining the properties of quantum objects. a possibility that would become central to quantum mechanics. As physicists struggled to understand the implications of wave-particle duality, they began to realize that the classical distinction between observer and observed might not apply in the quantum realm. The properties of light seem to depend not just on the light itself, but on the entire experimental context, including the measuring apparatus and the type of observation being performed. This holistic view of quantum phenomena would eventually lead to insights about the fundamental role of consciousness in determining physical reality. Einstein's resurrection of the particle theory of light had created a paradox that couldn't be resolved within the framework of classical physics. Light was neither wave nor particle in the classical sense, but something entirely new that transcended these familiar categories. This discovery opened the door to a deeper understanding of nature where reality exists in states of superposition until the act of observation forces it to manifest as either wave or particle, but never both simultaneously. The quantum revolution that began with Planck's blackbody formula and Einstein's photon theory would eventually transform every aspect of physics and lead to technologies that seemed like magic to earlier generations. But perhaps more importantly, it revealed that the universe operates according to principles far stranger and more wonderful than anyone had ever imagined. The classical world of solid particles and continuous waves was just the surface appearance of a deeper quantum reality, where the very act of observation helps to create what we observe. As we look back at Einstein's breakthrough, we can see the first glimpse of a universe where consciousness and physical reality are intimately connected. The wave-particle duality of light wasn't just a curious property of electromagnetic radiation. It was the first evidence that reality itself might exist in multiple states simultaneously, until observation forces it to choose just one form. The photons dancing through Einstein's photoelectric experiments were messengers from a quantum realm, where the distinction between potential and actual, between what could be and what is, becomes fundamental to understanding the nature of existence itself. Chapter 4: De Broglie's Cosmic Insight. Matter Waves. By 1924, the wave-particle paradox of light had been puzzling physicists for nearly 2 decades. Einstein's photons had successfully explained the photoelectric effect and proven that light carried energy in discrete packets, while Young's interference experiments continued to demonstrate the undeniable wave nature of electromagnetic radiation. Light seemed to be both wave and particle simultaneously, a contradiction that challenged everything scientists thought they understood about the fundamental nature of reality. But a young French prince named Louis de Broglie was about to make a leap of imagination that would transform this contradiction into something even more revolutionary. De Broglie wasn't content to accept that light was unique in exhibiting wave-particle duality. If nature was truly consistent, he reasoned, then the wave-particle relationship discovered for light should apply to everything else in the universe as well. In his doctoral thesis at the University of Paris, de Broglie proposed an idea so radical that it would eventually earn him the Nobel Prize and fundamentally reshape our understanding of matter itself. De Broglie's insight was elegantly simple, yet profoundly revolutionary. If light, which everyone had thought was purely a wave phenomenon, could behave like particles under certain conditions, then perhaps matter, which everyone assumed consisted of solid particles, could behave like waves under the right circumstances. This wasn't just a mathematical speculation. De Broglie was suggesting that every single particle in the universe, from the smallest electron to the largest planet, had an associated wavelength that governed its behavior in ways that classical physics had never imagined. The mathematics of de Broglie's hypothesis was surprisingly straightforward. Einstein had shown that photons carried energy equal to Planck's constant times their frequency, and that they also carried momentum despite having no mass. De Broglie realized that the relationship between momentum and wavelength that applied to massless photons might also apply to massive particles. He proposed that every particle with momentum p had an associated wavelength given by the simple formula lambda equals h divided by p, where h was Planck's constant and lambda was what came to be known as the de Broglie wavelength. At first glance, this idea seemed absurd. According to de Broglie's formula, a baseball flying through the air should have a wavelength, just like a photon or a sound wave. But when you actually calculate this wavelength, you discover why we never notice the wave nature of everyday objects. A baseball weighing 150 grams and moving at 30 meters per second has a de Broglie wavelength of about 1 times 10 to the minus 34 meters. This is unimaginably small, far smaller than the nucleus of an atom, and completely impossible to detect with any conceivable measuring instrument. The reason we don't observe wave behavior in baseballs, cars, or people is that their de Broglie wavelengths are so incredibly tiny that wave effects become negligible. It's like trying to notice the wave nature of water when the wavelength is smaller than the molecules themselves. The waves are still there in principle, but they're so small that they have no practical effect on the object's behavior. This explains why classical mechanics works so well for large objects. The wave nature of matter only becomes apparent when dealing with particles small enough that their de Broglie wavelengths are comparable to the size of the systems they're interacting with. But for electrons and other fundamental particles, the situation is completely different. An electron moving at typical speeds inside an atom has a de Broglie wavelength of about 1 times 10 to the minus 10 meters, which is roughly the same size as atoms themselves. At these scales, the wave nature of matter should become clearly observable, creating interference and diffraction effects, just like light waves passing through slits or around obstacles. De Broglie's thesis advisor was initially skeptical of this radical proposal. The idea that solid particles like electrons could behave as waves seemed to violate everything that classical physics had established about the nature of matter. But Einstein, when shown de Broglie's work, immediately recognized its profound importance. Einstein wrote that de Broglie had lifted a corner of the great veil that concealed the deeper mysteries of quantum mechanics. If de Broglie was correct, then the wave-particle duality wasn't just a strange property of light. It was a fundamental aspect of everything in the universe. The experimental test of de Broglie's hypothesis came through a series of remarkable accidents and insights. In 1925, 2 American physicists named Clinton Davison and Lester Germer were studying how electrons bounced off nickel surfaces at the Bell Telephone Laboratories. Their work was purely practical, aimed at understanding how electron tubes functioned in telephone equipment. They had no intention of testing exotic theories about matter waves or revolutionizing our understanding of quantum mechanics. But during one of their experiments, a glass apparatus containing their nickel target accidentally broke, exposing the hot nickel to air. The oxygen caused the nickel surface to oxidize, ruining their carefully prepared sample. To clean the surface and remove the oxide layer, Davison and Germer heated the nickel to very high temperatures in a hydrogen atmosphere. This heat treatment had an unexpected effect on the crystal structure of the nickel, causing the small individual crystals to grow larger and more perfectly ordered. When Davison and Germer resumed their experiments with the recrystallized nickel surface, they discovered something completely unexpected. Instead of scattering randomly in all directions, as classical physics predicted, the electrons were being reflected at very specific angles, creating patterns that looked remarkably similar to the diffraction patterns created when X-rays bounced off crystal surfaces. The electrons seemed to be behaving like waves that could interfere with each other and create the complex angular distributions that only wave phenomena could explain. At first, Davison and Germer didn't understand what they were seeing. The idea that electrons could diffract like waves was so foreign to their thinking that they initially assumed their equipment was malfunctioning, or that some unknown experimental error was creating the unusual patterns. But as they carefully repeated their measurements and checked their apparatus, they became convinced that they were observing a real physical phenomenon that classical physics couldn't explain. The breakthrough came when they realized that the nickel crystal was acting like a three-dimensional diffraction grating for the electron waves. Just as Young's double slits had created interference patterns for light waves, the regular array of atoms in the crystal was creating interference patterns for matter waves. The electrons weren't just bouncing off the surface like classical particles, they were diffracting through the crystal structure and interfering with themselves to create the observed angular patterns. The mathematics of this diffraction process followed exactly the same principles that governed X-ray crystallography. When X-rays hit a crystal, they scatter off the regular array of atoms and create interference patterns that reveal the internal structure of the material. The condition for constructive interference was given by Bragg's law, which related the wavelength of the radiation to the spacing between crystal planes and the angle of diffraction. Davison and Germer found that their electron diffraction data fit Bragg's law perfectly, but only if they assumed that the electrons had a wavelength given by de Broglie's formula. This was the first experimental confirmation that matter could behave like waves. The electrons in Davison and Germer's experiment were exhibiting the same kind of interference and diffraction effects that had convinced Young that light was a wave phenomenon more than a century earlier. But these electrons were definitely particles with mass, charge, and all the other properties that classical physics associated with solid matter. The wave-particle duality that had seemed unique to light was actually a universal property of everything in the universe. To make the confirmation even more precise, Davison and Germer carefully measured the strongest diffraction peak and calculated the corresponding electron wavelength using Bragg's law. They found a wavelength of about 1.65 times 10 to the minus 10 meters. When they used de Broglie's formula to calculate what the wavelength should be for electrons, with the energy they were using, they got exactly the same answer. The agreement between theory and experiment was so perfect that it left no doubt about the reality of matter waves. Around the same time, George Paget Thomson, the son of J.J. Thomson who had discovered the electron in 1897, was conducting similar experiments with high-energy electrons in England. Thomson was passing beams of electrons through thin films of crystalline materials and observing the patterns created when the electrons hit a photographic plate on the far side. Like Davison and Germer, Thomson found clear evidence of diffraction and interference, with the electron beams creating circular patterns of alternating bright and dark rings, exactly like those produced by X-rays or light waves passing through similar materials. The historical irony of this discovery was not lost on the physics community. J.J. Thomson had won the Nobel Prize in 1906 for proving that electrons were particles by measuring their charge-to-mass ratio and showing that they behaved like classical charge particles in electric and magnetic fields. 20 years later, his son George Thomson shared the Nobel Prize with Davison and Germer for proving that electrons were waves by demonstrating their diffraction and interference properties. As physicist Max Jammer wrote, one might feel inclined to say that Thomson the father was awarded the Nobel Prize for having shown that the electron is a particle, and Thomson the son for having shown that the electron is a wave. But this apparent contradiction wasn't really a contradiction at all. Both father and son were correct about the nature of electrons. Under some experimental conditions, electrons behaved like classical particles with definite positions, velocities, and trajectories. Under other conditions, they behaved like waves with characteristic wavelengths, frequencies, and interference properties. The electron was neither purely particle nor purely wave, but something entirely new that exhibited both aspects depending on how it was observed. The confirmation of de Broglie's matter waves opened up an entirely new realm of physics and technology. Scientists realized that the wave nature of electrons could be used to probe the structure of materials with much greater precision than light waves, since electron wavelengths were thousands of times smaller than visible light wavelengths. This led to the development of electron microscopes, which could reveal details of cellular structure and crystal arrangement that were completely invisible to ordinary optical microscopes. More fundamentally, the discovery of matter waves revealed that the classical picture of atoms as tiny solar systems with electrons orbiting around a central nucleus was completely wrong. If electrons were waves rather than particles, they couldn't follow definite orbital paths like planets around the sun. Instead, they had to be described as standing wave patterns surrounding the nucleus, with only certain wavelengths able to fit into the available space. This wave picture of atomic structure would soon lead to a complete understanding of chemical bonding, the periodic table, and the quantum mechanical principles that govern all atomic behavior. De Broglie's insight also extended far beyond electrons. Experiments soon confirmed that protons, neutrons, and even entire atoms could exhibit wave behavior under the right conditions. Otto Stern performed beautiful experiments in the 1930s using beams of helium atoms and hydrogen molecules, showing that even these relatively large objects could create diffraction patterns when passed through appropriately sized openings. The wave nature of matter wasn't limited to fundamental particles. It was a universal property that applied to everything in the universe, though it only became observable at very small scales. The philosophical implications of matter waves were staggering. If every particle in the universe had an associated wave, then the classical picture of reality as consisting of solid objects moving through empty space was revealed to be a crude approximation. At the deepest level, everything was wave-like, existing in states of superposition and exhibiting interference effects that classical thinking couldn't accommodate. The sharp boundaries between objects that we experience in everyday life were emergent properties that arose when countless quantum waves combined in complex ways. De Broglie's matter waves also suggested that the wave-particle duality wasn't just a strange quirk of light and electrons. It was pointing toward a fundamental principle about the nature of reality itself. Perhaps the universe was constructed from waves of possibility that could manifest as particles only when observed or measured. The mathematics of these matter waves would soon evolve into the wave functions of quantum mechanics, where the amplitude of the wave at any point gave the probability of finding a particle at that location. This probabilistic interpretation of matter waves was revolutionary. In classical physics, particles had definite positions and velocities at all times, even if we couldn't measure them precisely. But de Broglie's waves suggested that particles didn't have definite properties until they were observed. The wave described the quantum state of the particle, encoding all the information about what could be measured, but not determining any specific outcome until a measurement actually occurred. The wave nature of matter also provided the first hints about why atoms were stable. In classical physics, electrons orbiting around atomic nuclei should gradually lose energy by radiating electromagnetic waves and spiral into the nucleus in a tiny fraction of a second. But if electrons were standing waves rather than orbiting particles, they could exist in stable configurations where the wave pattern repeated itself exactly after each orbit around the nucleus. Only certain wavelengths could fit into these orbital patterns, explaining why atoms absorbed and emitted light only at specific frequencies corresponding to transitions between allowed wave patterns. As physicists began to understand the full implications of de Broglie's matter waves, they realized that the entire framework of classical physics would need to be replaced by a new quantum mechanical description of nature. The solid, deterministic world of classical particles moving according to Newton's laws was revealed to be an approximation that worked well for large objects, but failed completely at the atomic scale. The true foundation of reality was a quantum realm where everything existed as waves of possibility until the act of observation forced these waves to collapse into definite outcomes. De Broglie's doctoral thesis had done more than just extend wave-particle duality from light to matter. It had revealed that the universe was far stranger and more wonderful than anyone had imagined. Every electron in your body, every atom in the air you breathe, every photon that brings you the image of these words exists simultaneously as both wave and particle, embodying all possibilities until consciousness observes it into a single reality. The matter waves that de Broglie discovered were the first glimpse of a quantum universe where the boundaries between observer and observed, between potential and actual, between what could be and what is, become fundamental to understanding the deepest nature of existence itself. Chapter 5: The double-slit paradox, one electron's impossible journey. When Louis de Broglie proposed that matter possessed wave-like properties, physicists rejoiced at the birth of a new idea. Yet few suspected that this revelation would lead to one of the strangest discoveries in science. The classic double-slit experiment, first performed in the early 19th century by Thomas Young to demonstrate the wave nature of light, would, when revisited with single electrons, unravel assumptions about matter, energy, and the very fabric of reality. The modern version of the experiment seemed simple. A device emitted electrons one at a time toward a barrier with two narrow parallel slits. Beyond the barrier stood a detection screen sensitive enough to record the impact of each individual electron with a small flash of light or a digital click. Because the electrons were released individually, scientists could watch the pattern emerge one impact at a time. Classical physics predicted a straightforward outcome. Electrons, being particles with definite mass and charge, should travel through either the left slit or the right slit, much like marbles rolling through openings in a wall. Some would pass through one slit, others through the second, and the final image on the screen would be the simple sum of two single slit patterns. Two bright patches with a dim region between them. No surprises were expected. But when the experiment was actually carried out, the results defied logic. Instead of forming two bright bands, the electrons gradually produced a pattern of alternating bright and dark stripes, the unmistakable signature of wave interference, the same pattern Young had seen with light as more than 100 years earlier. Each electron struck the screen as a complete particle, never as a fraction of one, yet together they built an interference pattern identical to that of waves passing through both slits at once. When only a few electrons had arrived, the screen looked random, but after thousands and later millions of impacts, the precise wave pattern emerged with mathematical perfection. The dark regions were places no electron ever landed. The bright ones were where electrons most often appeared. This was impossible by any classical reasoning. How could a single electron, traveling alone, know about both slits? It seemed as though each electron somehow passed through both openings simultaneously and interfered with itself. The mathematics agreed completely with de Broglie's theory. The spacing of the bright and dark fringes depended on the electron's wavelength, the distance between the slits, and the geometry of the setup. The equations worked perfectly if, and only if, each electron was treated as a wave passing through both slits at once. Physicists soon asked the obvious question: what exactly was interfering with what? If only one electron was in flight at any moment, there could be nothing else to interfere with it. The only possible conclusion was extraordinary. The electron interfered with itself. The quantum wave describing its behavior spread through both slits, and the interference pattern revealed the probabilities of where the electron might be found when measured. The electron did not follow a definite path. It existed in a superposition of all possible paths until the instant of detection. To probe deeper, researchers introduced witch path detectors near the slits, hoping to determine through which slit each electron actually traveled. Classical reasoning predicted that such gentle measurements would not disturb the motion significantly. Yet every time the detectors were switched on, the interference pattern vanished. The electrons behaved as particles again, forming two bright spots as classical physics had predicted. When the detectors were turned off, even while physically present in the setup, the interference pattern immediately returned. It seemed that the electrons knew whether they were being observed. If unobserved, they spread like waves. If watched, they became particles. This so-called observer effect could not be explained merely by physical disturbance. The detectors measured with minimal energy exchange, often by detecting tiny electric fields or scattered photons, yet even this indirect measurement destroyed the interference. The mere availability of information about which path the electron had taken was enough to alter the outcome. Even more astonishing were the delayed choice experiments conceived decades later. In these tests, the decision to record or erase the which path information was made after the electron had already passed through the slits, but before it reached the detection screen. Strangely, the final pattern still depended on that late decision. It was as if the electron's earlier behavior adjusted itself to match what was decided later, suggesting a kind of retroactive influence that defied the normal flow of time. Such results struck at the core of our understanding of reality. They implied that an electron did not possess fixed properties like position or momentum until the moment it was observed. Before measurement, it existed only as a wave of possibilities, a mathematical function representing the potential outcomes. Observation seemed to collapse this wave of potential into one definite result. But what exactly counted as an observation? This question became the infamous measurement problem. Did collapse occur when the electron struck the screen? When a detector registered it? When the data were read by a human mind? The line dividing quantum uncertainty from classical certainty appeared vague and arbitrary. Some physicists suggested that consciousness itself might trigger the collapse. In that view, the universe remained in superposition until a conscious observer became aware of a measurement. This idea inspired Erwin Schrödinger's famous thought experiment, in which a cat sealed inside a box was both alive and dead until someone opened the lid. If awareness was required to fix reality, then consciousness would not merely observe the world, it would help create it. Other thinkers sought less mystical explanations. They proposed that interaction with the environment, known as decoherence, caused the collapse. According to this view, quantum superpositions constantly interacted with air molecules, thermal radiation, or other particles, losing coherence long before they reached human awareness. This explained why large objects never exhibited wave behavior, and why the everyday world seemed solid and definite without invoking consciousness. Yet, even decoherence could not fully account for the double-slit mystery. In carefully controlled conditions, vacuum chambers at near absolute zero temperatures, single electrons maintained their quantum coherence long enough to produce flawless interference patterns. Collapse appeared to depend not on environmental noise, but on whether information about the electron's path existed in principle. Niels Bohr described this dual behavior as the principle of complementarity. Quantum entities could display either wave-like or particle-like properties depending on the experimental arrangement, but never both at once. These two descriptions were mutually exclusive, yet jointly essential for a complete understanding of quantum reality. This duality extended beyond electrons. Photons, atoms, and even complex molecules consisting of hundreds of atoms have displayed interference patterns in modern experiments. As objects grow larger, their de Broglie wavelengths shrink, making wave effects harder to observe, but the principle remains universal. Every material object in the cosmos exists in a quantum superposition until observed. For this reason, the double-slit experiment is often called the heart of quantum mechanics. It encapsulates all the theory's paradoxes in one elegant demonstration. It reveals that quantum entities have no definite existence independent of observation, that probabilities replace certainties, and that the act of measurement itself determines what is real. Perhaps most unsettling, the experiment hints that the classical picture of an objective world existing independently of observers is incomplete. On the quantum scale, the boundary between observer and observed dissolves. The outcome of an event depends not only on what happens, but on how and when it is observed, and even on whether the relevant information is knowable at all. Modern variations of the experiment continue to deepen the puzzle. Scientists have performed quantum eraser tests showing that erasing witch path information can restore the interference pattern even after detection. They have demonstrated that the mere potential to obtain path information, even if never actually recorded, suffices to destroy interference. Some researchers have even tested whether human consciousness influences results by using automated random number generators to decide when which path data should be stored or erased. Every trial confirms the same conclusion. It is the physical availability of information, not awareness of it, that determines the outcome. Yet the profound question remains: what truly constitutes information in the universe? The double-slit experiment, simple yet profound, continues to challenge our deepest assumptions. It suggests that reality may not be a fixed collection of objects with definite properties, but a web of possibilities crystallized through interaction and observation. The wave function might not be a mere tool of calculation, but a description of an underlying quantum realm. A realm where all possibilities coexist, until the act of observation selects one. In contemplating this paradox, we are led to consider that consciousness and physical reality may be more intertwined than classical science ever imagined. The journey of a single electron through two slits invites us to glimpse a universe where observation and existence are inseparable, where the act of looking does not merely reveal the world, but helps to bring it into being. Chapter 6: The Measurement Problem. When does the wave become real? The electron double-slit experiment revealed something profoundly unsettling about reality. Particles seem to exist in multiple states simultaneously until they were measured, at which point they abruptly appeared as either waves or particles, depending on how they were observed. This strange discovery raised a haunting question. When exactly did this transition from the quantum world of superposition to the classical world of definite properties occur? Where was the boundary between the realm of possibilities and the realm of facts? This question became known as the measurement problem, one of the deepest mysteries in all of physics. In quantum mechanics, every system is described by a wave function, a mathematical expression encoding all possible outcomes of measurement. Before observation, a particle has no single position or momentum. It exists as a superposition of many possibilities. When a measurement occurs, the wave function appears to collapse into one definite result. But what counts as a measurement? What physical process triggers this collapse? And why do we not see superpositions in everyday life? Erwin Schrödinger dramatized the puzzle in 1935 with his famous thought experiment, Schrödinger's cat. He imagined a sealed box containing a cat, a Geiger counter, a bit of radioactive material, a hammer, and a vial of poison. The radioactive atom had exactly a 50% chance of decaying within 1 hour. If it decayed, the Geiger counter would detect it, triggering the hammer to shatter the vial and release the poison, killing the cat. If it did not decay, the cat would remain alive. According to quantum theory, before anyone opened the box, the atom was in a superposition of decayed and not decayed states. This entangled the entire system, Geiger counter, hammer, vial, and cat, so that the cat itself would be in a superposition of dead and alive. Schrödinger intended this scenario to expose the absurdity of applying quantum mechanics to macroscopic objects. Surely a cat cannot be both dead and alive. Yet the mathematics insisted otherwise. Physicists then struggled to pinpoint where quantum indeterminacy ended and classical definiteness began. Was it when the atom decayed? When the detector clicked? When the cat's fate was sealed? Or only when a human observer looked inside? Each stage was governed by quantum laws, yet the final outcome was always a definite cat, never a ghostly mixture of life and death. Some thinkers, notably John von Neumann and later Eugene Wigner, suggested that consciousness itself caused the collapse. In their view, the wave function remained in superposition until a conscious observer became aware of the result. The cat, then, would truly be both dead and alive until someone looked inside the box, at which point awareness forced reality to choose. This interpretation gave a clear answer. Collapse happens when consciousness intervenes, but it raised troubling implications. If observation determines a reality, then physical properties may not exist independently of minds. Without consciousness, the universe might remain an indefinite blur of probabilities. Many scientists recoiled from this idea. For centuries, physics has striven to describe an objective world existing independently of human perception. To make consciousness a necessary part of physical law seemed to undo that progress. Yet no purely physical explanation could fully solve the mystery either. In 1957, Hugh Everett proposed the many worlds interpretation, which avoided wave function collapse altogether. According to Everett, all possible outcomes of a quantum measurement actually occur, each in its own branch of reality. When the box is opened, one universe contains a living cat, another a dead one. The observer also splits, each version perceiving only its corresponding outcome. In this picture, the universe continually divides into countless parallel worlds. From the perspective of the multiverse, quantum mechanics is entirely deterministic. Nothing truly random ever happens. The many worlds theory elegantly sidestepped the collapse problem, but demanded belief in an unfathomable number of unobservable universes. Every quantum event, even the decay of a single atom, would spawn new branches of reality. It explained the mathematics, but strained credulity. A more grounded solution came through environmental decoherence. Real quantum systems are never isolated. They constantly interact with their surroundings. Air molecules, photons, and electromagnetic fields. These interactions rapidly entangle the system with its environment, scrambling the delicate phase relationships that enable interference. As a result, superpositions become effectively unobservable. The system appears to collapse into a definite state, even though, strictly speaking, the underlying evolution remains smooth and deterministic. Decoherence explains why we never see quantum superpositions in macroscopic objects. A cat, composed of trillions of atoms and immersed in a warm, noisy environment, decoheres almost instantaneously. Any potential superposition is destroyed before it can be detected. In this way, classical behavior emerges naturally from quantum principles, without invoking consciousness or modifying the laws of physics. Yet decoherence does not fully resolve the measurement problem. It explains why interference disappears, but not why one specific outcome is realized. The mathematics predicts that all possibilities remain present in principle, merely hidden from observation. The transition from many possible to one actual remains conceptually mysterious. Some scientists believe this indicates that quantum mechanics is incomplete. Hidden variable theories propose that particles always possess definite properties, determined by unseen parameters. The apparent randomness of measurements would then arise from ignorance of these hidden details. But in 1964, John Bell demonstrated that any such local, hidden variable theory would contradict the predictions of quantum mechanics. Experiments testing Bell's inequalities consistently confirmed the quantum results, showing that nature itself is either non-local or fundamentally indeterminate. Reality, it seems, defies classical logic. Modern experiments have pushed these mysteries further. Researchers have created quantum superpositions of increasingly large systems, molecules, mechanical resonators, even superconducting circuits visible to the naked eye. They have entangled clouds containing trillions of atoms, showing that quantum effects persist at scales far larger than once imagined. No experiment has yet revealed a clear boundary where quantum mechanics ceases to apply. The quantum Zeno effect adds another twist. Frequent observation can actually prevent a quantum system from evolving. Repeated measurements continuously collapse the wave function, freezing the system in its initial state. Observation itself, then, is not passive, but actively shapes reality, an eerie echo of Zeno's ancient paradox of motion. Some interpretations embrace this mystery as a clue to something deeper. They suggest that the classical world is not fundamental at all, but an emergent approximation, of an underlying quantum reality. Consciousness, rather than being an accidental byproduct of physical processes, might play an essential role in transforming quantum potential into actual experience. The act of observation could be the creative moment through which the universe becomes real. The measurement problem is not merely philosophical, it has practical consequences. Quantum computers depend on maintaining coherent superpositions of quantum bits. Any unwanted measurement, or even slight environmental interaction, destroys this coherence through decoherence, collapsing the computation prematurely. Understanding the measurement process is therefore crucial to building reliable quantum technology. Recent quantum eraser and delayed choice experiments have deepened the puzzle further. In these setups, decisions made after a measurement can appear to influence outcomes recorded earlier, blurring the line between cause and effect. The boundaries between observer and observed, past and future, seem far more fluid than classical intuition allows. Ultimately, the measurement problem forces us to reconsider what we mean by reality. Perhaps observation is not a mere act of perception, but a fundamental interaction that brings one version of the universe into being. The distinction between subject and object, between mind and matter, may be less absolute than it appears. Whether the answer lies in new physics, new mathematics, or new insights into consciousness remains unknown. But one truth endures. The quantum measurement problem has revealed that existence itself, what it means for something to be, is far more mysterious, dynamic, and intertwined with observation than anyone ever imagined. Chapter 7. The Quantum Cheshire Cat. Separating properties from objects. Quantum mechanics has always challenged our ideas of reality, but one of its strangest discoveries suggests that the very properties of objects can exist apart from the objects themselves. This baffling effect, called the quantum Cheshire Cat, borrows its name from Alice in Wonderland, where the Cheshire Cat fades away, leaving only its grin behind. Physicists have found that something similar can happen in the quantum world. A particle and one of its properties, such as spin or polarization, can become separated, each existing in a different place. This revelation is forcing science to rethink what it means for anything to possess a property at all. In daily life, properties are inseparable from the things that have them. The color red belongs to an apple, the hardness belongs to a rock. It seems nonsensical to imagine a color or hardness existing in space without an apple or a rock attached. Yet quantum mechanics has repeatedly overturned such intuitions. It has shown us that particles can be in multiple locations at once, and that distant particles can instantaneously influence each other. Now, it tells us that properties can detach from their objects entirely. The foundation for this discovery lies in a special kind of quantum experiment known as a weak measurement. In traditional quantum measurements, observing a system collapses it into a definite state, erasing all quantum superpositions. Weak measurements, however, gently extract partial information without destroying the system's delicate quantum coherence. They allow scientists to peek into the in-between world that exists before a particle is forced to choose a single outcome. A helpful image is that of measuring the speed of a soap bubble. If you hurled ping-pong balls at it, you would pop the bubble and ruin your experiment. But if you brushed it lightly with feathers, you might learn something about its motion without bursting it. Weak measurements are the quantum equivalent of using feathers. They disturb the system so little that it retains much of its quantum strangeness. Using these techniques, physicists discovered that different aspects of the same quantum object could behave independently. Instead of asking the system a blunt yes or no question, weak measurements revealed how various properties, like position and polarization, could occupy distinct regions of space. This hinted that the connection between an object and its attributes might not be as tight as classical physics assumes. The key breakthrough came when researchers at the University of Vienna and elsewhere performed weak measurements on single photons. They prepared photons in superpositions where each could be in two places at once, and its polarization could point in two directions simultaneously. Classical reasoning would say that If the photon's polarization belongs to the photon, the two must always appear together. Yet, the experiments revealed something startling. The photon's physical presence, the bit that could strike a detector, was found mostly in one place, while its polarization appeared mostly in another. The photon and its property had parted ways, just like the Cheshire Cat and its grin. This was not a trick of mathematics or a flaw in the instruments. The researchers could even manipulate the polarization independently, rotating it where the photon itself was not, and the separated property responded as though it truly existed on its own. It seemed that a photon's polarization could act as a free-floating entity, detached yet still physically effective. Such findings forced physicists to reconsider the basic idea of an object. In classical thought, an object and its properties form an inseparable whole. But at the quantum level, they can disassociate. Properties such as position, spin, or energy can each occupy their own spaces, all quantum mechanically linked, but not confined to one point. The familiar unity of an object appears to be a product of our macroscopic viewpoint, not an absolute feature of nature. Subsequent experiments extended the effect further. Researchers managed to separate multiple attributes, like a particle's spin, charge, and momentum, spreading them across different regions of space. These ghost properties were not passive shadows. They could interact with other quantum systems, cause interference, and alter measurement outcomes. Detached properties retained all the causal power of ordinary ones, even without their original carriers. The quantum Cheshire Cat offered a new perspective on the long-standing measurement problem, the puzzle of how observation creates definite outcomes. It showed that measurement not only collapses possibilities, but can redistribute an object's properties across space and time. Reality does not simply reveal itself through observation, it may reconfigure itself as a result. This realization deepened the implications of Bell's theorem, which had already demonstrated that quantum mechanics cannot satisfy both locality and realism. The Cheshire Cat effect suggested an even more radical non-realism. Not only do properties lack definite existence before measurement, but they can exist separately from their supposed owners. The same logic shed new light on entanglement. When two particles become entangled, their properties are mysteriously linked across distance. The Cheshire Cat effect implies that these correlations might reflect actual transfers or sharing of properties through space without any particle carrying them. Properties could roam independently, connecting distant regions of reality in subtle, non-local ways. Some physicists began to see these results as pointing toward a deeper informational foundation of the universe. Perhaps information, encoded in properties like spin or polarization, is more fundamental than matter itself. In that view, particles are temporary vessels for information, not the other way around. Matter might emerge from the interplay of free-floating properties that sometimes gather into what we perceive as objects. Beyond its philosophical impact, the quantum Cheshire Cat could have practical applications. If scientists can control and separate quantum properties, they might build new types of quantum computers that process information in parallel through distinct spatial channels, without requiring all qubits to be in one place. Likewise, quantum communication could use detached properties to transmit information without moving entire particles, potentially creating faster, more secure links. Since these properties are less prone to environmental noise, they might outperform conventional methods of quantum data transfer. Researchers have also begun using the Cheshire Cat effect as a diagnostic tool to probe quantum foundations more deeply. By tracking separated properties, they test how far the division between an object and its attributes can stretch. Can a property be detached across great distances? Are there natural limits to such separations? These questions push experimental physics into new conceptual territory. Even more astonishing are recent experiments showing temporal separation, cases where a particle's property appears at a different time than the particle itself. A property measured earlier or later can still correspond to a particle that seems to exist elsewhere in time. This hints that quantum reality may blur not only spatial boundaries, but also the very sequence of cause and effect. The philosophical stakes of these findings are immense. Classical philosophy assumed that properties depend on objects or on relations between object and observer. The Cheshire Cat experiments propose a third possibility. Properties may exist as independent realities, neither belonging to objects nor depending on observation. If so, then identity itself becomes a puzzle. What is a particle if its properties can wander freely? Perhaps a particle is nothing more than a temporary meeting point of properties, a dynamic pattern rather than a fixed thing. Some thinkers even connect these ideas to consciousness. Maybe consciousness, too, is a kind of property that can exist separately from its apparent physical host, the brain. The way properties detach from particles could parallel the way awareness might transcend its biological vessel. Though speculative, such ideas show how the Cheshire Cat effect bridges physics and philosophy in unexpected ways. As research continues, evidence mounts that this separation of properties may not be rare but fundamental. The solid, unified world we perceive could be an illusion born of limited perception, a composite of countless scattered quantum properties that only appear coherent on a large scale. The classical universe, with its firm boundaries and enduring objects, may be a convenient mirage produced by quantum entanglement and averaging. The quantum Cheshire Cat thus stands as one of the most astonishing revelations in modern science. It tells us that reality is not made of stable things, but of shifting patterns of attributes that can appear, disappear, and drift apart like the grin of a cat in the quantum mist. It forces us to ask whether anything truly exists as an object, or whether all existence is simply a dance of properties, momentarily joined before parting again. In this strange light, our world looks less like Newton's clockwork and more like Alice's Wonderland, a realm where logic bends, boundaries blur, and the act of observation itself helps shape what is real. Chapter 8: The Observer Effect and Consciousness. The quantum Cheshire Cat effect revealed something astonishing: that properties could exist separately from the objects they belong to. This idea upended our deepest assumptions about reality and raised a profound question. What role does consciousness play in shaping what becomes real? Quantum mechanics, from its earliest days, struggled with the mystery of measurement. The theory's mathematical framework, built upon wave functions, described smooth and deterministic evolution according to the Schrödinger equation. These wave functions represented probabilities, not certainties, and could exist in perfect superpositions indefinitely. Yet every experiment yielded a single, definite result. Something seemed to intervene when observation occurred, collapsing possibility into actuality. This puzzle, the measurement problem, haunted the founders of quantum theory. The mathematics could predict the odds of outcomes with uncanny accuracy, but could not explain why one outcome became real instead of another. If quantum systems truly remained in superposition, why did measurement yield only one result? What mechanism forced the collapse? Werner Heisenberg and Max Born recognized that measurement involved an interaction between a quantum system and its measuring apparatus. But since measuring devices were themselves made of quantum particles, where exactly was the line between quantum and classical worlds drawn? If both observer and instrument were quantum systems, why didn't everything remain in superposition? Some physicists proposed a radical idea that consciousness itself triggered collapse. Human observers never experienced superpositions. Each person always saw one definite result. This suggested that consciousness might play a unique role in forcing reality to crystallize out of the quantum fog. John von Neumann developed this interpretation mathematically. He described an infinite chain of interactions, from the measured system to the device, to the recording instrument, to the observer's senses and brain. Each link should remain quantum, endlessly entangled, unless something outside the physical framework intervened. To stop this infinite regress, Von Neumann postulated that consciousness existed beyond quantum mechanics and could collapse wave functions through observation. Under this view, consciousness marked the boundary between the quantum and classical realms. Physical systems stayed in superposition until observed by a conscious mind. Thus, reality was not an objective, fixed structure, but a participatory process co-created by consciousness itself. Eugene Wigner expanded this idea through his famous thought experiment, Wigner's friend. Suppose his friend made a quantum measurement in a sealed lab. To the friend, consciousness caused the collapse into one definite outcome. But for Wigner, who remained outside, the entire lab, friend included, should stay in superposition until he observed it. Whose observation truly determined reality? This paradox hinted that consciousness might be more deeply woven into physics than anyone had imagined. Yet many scientists resisted this notion. The scientific enterprise depends on objectivity, on the idea that results do not depend on who observes them. If consciousness determined outcomes, objectivity itself would collapse. Critics noted that modern quantum experiments were often automated. Particle detectors, computers, and recording instruments operated without human oversight. These devices still produced definite outcomes. If consciousness were required, such automated measurements should yield indefinite results, yet they did not. Proponents countered that collapse occurred only when conscious beings eventually examined the data. Until that moment, they argued, the experiment existed in a superposition of all possible outcomes. Only awareness converted probability into fact. To test these claims, researchers designed increasingly precise experiments. Some used random number generators to decide when to measure, removing conscious timing. Others involved unconscious patients or animals as observers. Yet results remained ambiguous. It proved nearly impossible to separate the effects of consciousness from those of physical interaction. Every act of observation, even by a human, involved photons, nerves, and matter, blurring the line between mind and mechanism. Decoherence theory later offered a powerful alternative. It showed that superpositions are destroyed when quantum systems interact with their environments, with air molecules, radiation, or thermal noise. This process explained why superpositions become unobservable without invoking consciousness. The environment, in effect, continually measures everything. However, decoherence still failed to explain why one specific outcome occurs rather than another. It made superpositions invisible but not non-existent. A different school of thought, called quantum Bayesianism or cubism, reframed the problem entirely. According to cubism, quantum mechanics does not describe objective reality, but represents an observer's personal beliefs about possible outcomes. The wave function is not a physical entity, but a mental tool, a way to calculate expectations. Collapse, then, is not a physical event, but the observer's mental update upon learning new information. Reality becomes fundamentally subjective, grounded in experience, rather than in detached observation. Quantum experiments have only deepened these mysteries. Quantum erasure and delayed choice experiments show that whether a particle behaves like a wave or a particle can depend on information obtained after detection. Observation, or more precisely, the availability of information, determines what kind of reality emerges. This implies that knowing, not merely seeing, plays a decisive role in shaping outcomes. Still, the question remains, what is information, and who or what possesses it? Does information require a conscious knower? If so, consciousness might be essential not for collapse itself, but for the very existence of information. Some researchers have gone further, proposing that consciousness is inherently quantum. Roger Penrose and Stuart Hameroff's orchestrated objective reduction theory suggests that quantum computations in microtubules within brain cells produce conscious experience. According to their model, these quantum processes could influence physical reality directly. Most neuroscientists, however, remain skeptical. They argue that the brain's warm, noisy environment would destroy quantum coherence almost instantly. Yet proponents counter that biology may have evolved mechanisms to protect quantum states, allowing consciousness to function through quantum principles unknown to classical physics. Other perspectives take a more balanced approach. Participatory realism, for instance, views the universe as a collaboration between quantum systems and conscious observers. Consciousness does not create the world from nothing, but helps actualize one outcome from many possibilities. Reality, in this view, emerges from interaction, a cosmic partnership between mind and matter. The idea of global or collective consciousness has even been tested. Researchers have distributed quantum random number generators around the world and searched for correlations with moments of intense shared human emotion, natural disasters, global celebrations, or acts of violence. Some claim to find subtle deviations from randomness during such events, suggesting that collective attention may influence quantum outcomes. Others argue these findings result from chance, bias, or instrument error. The debate continues, balancing on the edge between science and speculation. These questions also touch the future of artificial intelligence. If consciousness truly collapses wave functions, then conscious machines might require quantum foundations. Perhaps only systems that exploit quantum processes can host subjective experience. Others maintain that consciousness could arise from any sufficiently complex information system, whether classical or quantum. Ultimately, the observer effect forces us to reconsider the relationship between mind and matter. Classical physics treated consciousness as an incidental byproduct of neural complexity, a passive witness to a mechanical universe. Quantum mechanics, by contrast, hints that consciousness may be a fundamental ingredient in the recipe of reality itself. Whether it collapses wave functions, participates in actualizing possibilities, or merely experiences the unfolding of an independent world, consciousness appears inseparable from the structure of existence. The clear division between observer and observed, so firm in Newtonian thought, dissolves in the quantum realm. Perhaps the ultimate lesson of the quantum theory is that consciousness and the physical universe are not two separate things, but two faces of a deeper unity. The act of observation, the meeting point between awareness and the world, may be the creative engine of reality, the eternal dance through which possibility becomes experience. Chapter 9: Reality as Pure Information, the Deepest Level. The strange link between observer and observed revealed by quantum mechanics hinted that consciousness and reality were far more intertwined than classical physics had ever imagined. Yet as scientists probed deeper into the mathematics of quantum theory, they uncovered a truth even more radical. Everything that exists, matter, energy, space, and time, might ultimately be patterns of pure information processed by the universe itself. This idea was most powerfully expressed by John Archibald Wheeler, one of the visionary physicists of the 20th century. A collaborator of Einstein and mentor to Richard Feynman, Wheeler coined terms such as black hole and wormhole, but his most daring proposal came in the 1980s when he declared that reality itself might be informational rather than material. His famous phrase, "it from bit," suggested that every physical it, every particle, field, or event, arises from fundamental bits of information. Matter and energy, according to this view, are not the building blocks of the cosmos, but emergent properties of underlying informational processes. Quantum information theory soon gave this philosophical vision mathematical depth. Scientists discovered that quantum systems could store and manipulate information in ways impossible for classical systems, giving birth to quantum computing and quantum communication. In classical physics, bits exist as either 0 or 1, but quantum bits, qubits, can exist in superpositions of both states simultaneously. This allows quantum information to encode vastly more possibilities and to process them in parallel, providing insight not only into computation, but into the very nature of reality. The familiar wave-particle duality could now be reinterpreted, as two modes of information processing. The wave represents distributed, parallel information, while the particle represents localized, definite information. When a quantum system is measured, it does not physically collapse but transitions from parallel to serial information processing, a reorganization of information rather than a mechanical event. The act of observation thus becomes an informational exchange, in which the observer gains knowledge and the system restructures itself accordingly. Further evidence for the informational nature of reality appeared through the holographic principle developed in the 1990s. Studies of black holes revealed that all information contained within a volume of space could be fully encoded on the two-dimensional surface enclosing it. The universe, then, might resemble a cosmic hologram, our three-dimensional world, a projection from a two-dimensional informational boundary. Everything we perceive as solid or tangible could be emergent data from this deeper holographic code. In this vision, even consciousness may be a holographic phenomenon, a projection from an informational substrate beyond space and time. Wave-particle duality fits naturally here. The wave is the distributed information on the boundary. The particle, the localized projection within space. Reality becomes a vast holographic computation, continuously converting information into experience. Quantum error correction strengthen this perspective. To protect delicate quantum data from noise, physicists devise methods that distribute information across many qubits, so that local errors cannot destroy it. Some theorists propose that the universe employs similar error correction to preserve the consistency of physical laws. The masses of particles, the strengths of forces, and the so-called fine-tuning of nature may all reflect parameters in a self-correcting informational code, an immense quantum computation maintaining cosmic stability. Digital physics extended the concept still further. It proposed that the universe is a kind of computer, processing discrete units of information according to simple computational rules. Space and time may not be fundamental entities, but emergent properties of this cosmic computation. In some models, the universe resembles a vast cellular automaton, a network of simple updating nodes whose interactions generate the complex patterns we call physical reality. The laws of physics could then be seen as high-level descriptions of the statistical behavior of countless informational operations. From this viewpoint, quantum superposition corresponds to parallel computation exploring many possible outcomes. And wave function collapse marks the moment those computations converge on a single result. The apparent randomness of quantum mechanics may arise from the finite limits of information processing within this cosmic computer. Quantum entanglement added yet another layer to the story. When two particles become entangled, their shared information transcends space and time, allowing instant correlations regardless of distance. What Einstein once called spooky action at a distance may be natural if the universe is an informational network in which all parts are connected through shared data structures. Separate objects, from this perspective, are not truly separate. They are localized expressions of a unified field of information. Recent developments in quantum foundations have pushed this informational view even further. Researchers have shown that the entire mathematical framework of quantum mechanics can be reconstructed from simple principles about how information is acquired and processed. Space, time, matter, and energy thus appear as emergent phenomena arising from deeper informational laws. Our tangible world might be the user interface of a cosmic information system, much as a computer desktop presents icons and images that conceal the underlying code. This shift carries staggering implications. If reality is informational, then the boundary between physical and digital, between real and virtual, becomes fluid. Advanced civilizations, or perhaps consciousness itself, might learn to hack the cosmic code, manipulating the underlying information that defines physical existence. Quantum computers represent the first primitive tools for accessing this deeper layer. By exploiting superposition and entanglement, they can perform tasks that would take classical computers longer than the age of the universe. More profoundly, They teach us that information itself, not matter, is the true currency of reality. Some thinkers speculate that sufficiently advanced quantum computers could simulate entire universes, creating self-consistent realities indistinguishable from our own. If so, our universe could itself be a simulation within an endless hierarchy of informational worlds, each level both creator and creation, each bound by its own computational limits. These ideas naturally lead to questions about consciousness. If consciousness is an informational process rather than a material substance, then identity might persist across different substrates of computation. Death could then be seen not as annihilation, but as transformation, a shift from one mode of information processing to another. Some interpretations even propose that all possible informational patterns exist simultaneously, forming a vast cosmic library of realities. Consciousness, in this view, is the process through which specific patterns become self-aware within that infinite informational field. Mathematics gains new significance in this picture. Its uncanny power to describe nature might arise because the universe itself is mathematical. Reality written in equations rather than built from particles. Human understanding of mathematics may reflect the mind's resonance with the underlying informational structure of existence. Our growing mastery of science and technology may thus represent consciousness awakening to its own computational nature within a mathematical cosmos. The future of civilization could hinge on how deeply we comprehend and harness these principles. As quantum technologies mature, humanity may learn to participate directly in the cosmic computation that generates reality. The once mystifying wave-particle duality might become the key to manipulating the informational fabric of the universe itself. The informational paradigm also reframes ancient philosophical questions. Why does anything exist rather than nothing? Because information requires difference and structure, pure nothingness cannot compute. The Big Bang, from this standpoint, was the initialization of cosmic information processing, not the creation of matter from void. Why does the universe seem fine-tuned for life and consciousness? Perhaps because consciousness is not an accident, but the intended outcome of the cosmic computation, a universe designed to know itself. We have journeyed from Newton's corpuscles to Young's waves, from Einstein's photons to Wheeler's it from bit. The progression reveals a profound unity. Consciousness and cosmos are two sides of a single informational process. We are not observers standing apart from reality, but integral nodes in the universal computation that brings reality into being. The dance of particles and waves is, at its deepest level, the dance of information and awareness, pure consciousness expressing itself through the infinite algorithms of existence.